Hello and welcome, I'm Jono, and today I think I'll be looking at a bit of code optimization. So my intended audience here will be people who are not beginner programmers, maybe like you're big O, you've chosen a suitable algorithm and you've hit a bottleneck despite that, and you're like, now it's time to squeeze some performance out. So we're just going to go in there and like fiddle with bits of code, get everything running very, very smoothly. So I probably do like 2 or 3 tips, like exciting tip for code optimization, the results will surprise you, something like that. I'll be working with Golang as an example, but everything I'm going to do is going to be completely generic. It should be applicable for any programming language. And in particular, I've chosen a sort program. Like it's the Golang sort from like 2 or 3 years ago. That was their standard library sort. A couple of years ago, they replaced it with a new one, and it had a big performance uplift. So the first tip I'll probably give is one that will bridge that gap. Let's get stuck in, shall we? All right, first thing to do, here it is the sort program. I've just pasted in the code from the standard library. What we're going to be doing is benchmarking first, because we need to see what the performance is, or else we can't know if it improves or not. So I've got a benchmark result. In Golang, you can just make benchmark tests. So again, I've copied this from the standard library. The benchmarking test, let's rerun it. You set it up with multiple runs. In this case, I've done with powers of 10, so anywhere from 100 to 10 million length array is going to get sorted. And what it will do is it kind of, it runs it to a fixed length of time. So the ones that are only 100 length will get run many, many times. The ones that are really long and take longer aren't run as often, and so the results will be less accurate. But the idea is that you then get standard benchmark results with nanoseconds per operation. So we want that number to go down. I've taken this first one here, so this is the main sort algorithm. I'm also benchmarking the individual insertion sort, which is the base case. So if you know quicksort, it runs through the array, puts the smaller numbers to one side, larger numbers to the other, and then it repeats on those. And so it's like a tree. And then instead of going all the way down into lengths, like length 2, and trying to sort them into smallest and largest, it stops much earlier and flicks to an insertion sort, which is your base case one. So there's 2 parts to it. But let's look at optimizing the overall speed first. And so if we have a look, I have put this in here with a chart. Cool, number goes up as expected with bigger arrays. It will start taking longer. Then the next thing to do is to see where our bottleneck is, so we know where to work. So let's just do, in fact, let me show you. There is a profiler. That's the insertion sort being profiled. This is the other test being profiled. This is a one-off test. So as I said, the benchmark is going to run it multiple times and basically try and get a fixed duration. That means each of those runs, whether it's the short array or the large one, are getting an equal amount of compute time. So when you look at how long some operations are taking, if you've sped them up, it's actually just going to pad them out. It's going to run more often to fill in the extra time. So you won't see individual times going down, which is not what we really want. So for comparison, I've done a separate test, like 10 million length array. It's just sorted. And I think, just in case it gets a bit dodgy, some random numbers, make sure there aren't too many duplicates is what I was just doing there. Okay, so we've run it again. Let's now go use profiling tool. So for your language of choice, hopefully you've got a way of inspecting how long individual commands are taking. It's called pprof in Golang. To pprof, and we want to do sort.prof. So the first thing to do is to list everything that's taking the longest amount of time. We've got do pivot is taking the most. That's where it splits it into the lower half and the greater half, so that makes sense. The insertion sort base case is way down the end. Okay, fine. And then other things, some calls to the less function. Fair enough. Let's list do pivot. So this is a code listing, and it will show the execution time for each. So if we have a look, for each of things that are within this function, how long they take, a total of 1.3 seconds, and including sub-process calls, the cumulative amount is going to go up to 1.93. So we're looking for a big number here, big number, well, okay, straight up. In fact, if it's going to be a second long, that is almost all of it. So this is where it is doing reads and doing less. So it goes down the array, and then when it finds, it wants to put smaller ones on one side, larger on another, finds ones that are out of place, finds one of each, and then it swaps them down here. So the slow part, the really slow part, is actually in the comparisons only, not in the swapping. So it's as it walks up and down. Total time spent, does that even add up? It does it up to 2, fair enough. So it spends about 1 second in here, which will be doing little comparison things. And it spends another 200 milliseconds there, 200 there, another half second. So there's our first optimization. It's easy. It's clearly not inlining, right? We want to get rid of function calls. So it is calling data.less, and it's coming out of it because it's doing some time in a subprocess call. And in an ideal world, these things would be inlined. If we have a look at it, it's like a trivial function. Here's the interface. It's saying is I less than j. So this interface is kind of the entire data structure. It's like a slice or a vector. And the less function says your item at I and your item at j. Is that one less? If we actually look at the implementation, it's just return I is less than j. So it's a nothing op. So that should get inlined by the compiler, right? You need to understand that we aren't telling the computer exactly what to do. We're talking to the compiler through programming language. The compiler decides exactly what operations get made. So we ought to have told the compiler it can inline that. That's really small, but we can check this. So just let's remember these numbers right now. Well, we can see it, I suppose. It's 200 milliseconds there, 200 there. I should be able to say go no inline. I think that's correct. So I'm just trying to validate that the issue we're having is the fact that it's not inlining the less function. So now I'm forcing it to not inline it, and I'll check that it still has a bad result. Right. Let's go back in and let's do pivot again. Find our hotspot. I mean, it's about the same. So this one's gone higher. It's off by 160. This one is still off by 100 and something. Yeah, okay. Look, it ran a bit slower, but it's about the same. More or less 200 milliseconds for each of these. So for some reason, it's not inlining that less call. Now, we don't have to sit here and fret and wonder exactly why that might be. Let's just inline it ourselves. We have the power. We have the power of search and replace. So we're not going to need the interface. We're going to get rid of that entirely. Instead of the interface, we're just going to use int slices. Let's just do that first. So let's go to all the interfaces and turn them into int slices. Looks like the AI is off. Maybe it's my internet connection. All right, well, it's not clear why cursor's turned off, so I had to do this the manual way, which is a bit rubbish. So we're going to be doing data j. Oh my God, this is so slow. Yeah, come on. Convert all less calls to use less than operator. It's clearly working, but I'm not getting any recommendations in here. God, it's so slow. Ah, we're off. Pivot less, yes. Pivot less than B. Whoa, hold up. Oh yeah, it's going to put the not on the outside. You can just use a greater than operator, but fine, whatever. That was really clunky. Why are inline suggestions not working? shell sort. Fine. Okay. So that was a bit of a chore, but we have avoided the need for inlining. We just manually inlined it. Top do pivot. We are sitting on, a lot of other stuff's disappeared. Oh, notice this, the median of 3 has been inlined. Nice, maybe I've taught it to start inlining some things. Let's do pivot. There we are. This is the same line. Now it is no external function call, so the two numbers are identical, right? What's being done in this function is everything. There's no sub-process. And that's down by about, so that's similar, but this one's about 400 milliseconds shorter. The whole thing's down by a lot more than that. That's a big savings. Okay, so let's put the benchmark numbers in. Sort with inline less. Yeah, and there we go. It's pretty much exactly half as long, double the speed. Yeah, interestingly, linear line, which is kind of odd for a sort function, but for the benchmark, there is a pattern to it because it's deterministic, so maybe it's just hitting the base cases early, or yeah. I'm not going to dig into it. We're here to tune. We're not here to do algorithmic changes or to understand exactly what the input is doing. We're here to tune code. So that's number 1 done. Next, I thought we'd have spend some time looking at insertion sort, which is like the base case. So that's why I made a separate benchmark of it. I've got a separate benchmark test. In fact, let's just put that up. Let's just make the chart. I have room for it in the spreadsheet. There we got it. Okay, this one is a bit more of that sort of quadratic look. So kind of a little bit more like what we would be expecting. So let's have a look at what happens. Preprof of insertion sort. It's we've managed to get it up to a large enough time, but it's been inlined. So if I do a list of, we'll probably only see function calls to it. Insertion sort takes 660 milliseconds, so it doesn't tell us much. Okay, no, hang on. The inlined amount has been broken out. Nice. And it just spends all its time doing comparisons. But actually, some of that will be the line underneath it as well. Still, most of the time it believes is in that comparison line. Trick number 2. So what this is doing, insertion sort, is just, it's really basic. It's a for loop, 2 for loops. And what it's doing is it's got a sorted little piece of it, of the array that's slowly growing. That's the outer loop. And each time it wants to grow it finds one array item, it percolates it down, swapping, until it finds the spot it belongs in, and just does that with each one. So the problem, and what's not optimized here, is the fact that it's reading and writing from memory in a really inefficient way. So in the computer systems, you've got a cache. So the main memory is slow, and it's your large main memory, and then with it, for each CPU, you've got faster pieces of memory called cache that you can kind of work on as like a local scratch pad almost. So they're a lot quicker for accessing in particular, but because they're more local to the CPU, when you write to it, you get this issue with it being dirtied. So a dirty cache means that some CPU, maybe another one, has written to it. You can no longer be too sure what's happening there. So your next read is going to have to refresh the cache from main memory. To make things go quicker, what you want to do is a whole lot of reads with no writes. That means you're reading from the fastest cache possible before you dirty it. Let's change what it's doing. Instead of this bubble down, this happens with anything, right? You're doing these read modification. So do all your reads first, do your modifications second. This one's going to work fine because we can find the place it belongs with a whole lot of reads without doing the bubbling, then do all the shift and the reading. So let's just type this out here. We're going to go do all reads first. The AIs is off. Maybe like Cloudflare's down. Cloudflare? I don't know. Something's down. So we're in manual mode. ith1 is going to be shifted down. So straight up, we can just compare that value all the way down. Let's make j equal to I here, because we're going to save the place that we're going to. Grand. That works. Get rid of that. Okay, so that's all the reads in one place. And now we have to do the writes. So what we're going to do, before it was bubbling things up, we're going to take that whole piece and shift it up in one go without reading, writing. So for that, we can use a copy operator. And for copy, you write the destination first. So this is going to be one higher. Are we allowed to go to I+1? Yeah, that means the ith position, that last one we did. And we're going to copy from data j to I. And then, so we've moved up and there's a gap at the beginning. So data at whatever our jth position that we got to is going to be equal to the value. So the specifics don't matter, right? It's just insertion. Whether you follow that or not doesn't matter. The main thing is that the reads occur here, up the top. There's no writing out to data, only reading from it. And then we do all the writing with no further reads, actually, just the one big read for copy, which is nice. But the main gain should be in those reads, which is where we saw most of the time being taken. In fact, while we're doing this, let's just save this code and run it. This will all happen much quicker. This bit down here probably will be quicker because it's one call, but you don't always manage to do that. It's making a fast read section. Let's see how we have done overall. Okay, so if this is old insertion, now we've got insertion, like read, write. Read then write is kind of what I'm trying to say. And yeah, I mean, it's a huge savings once you get long enough. Down low where it's short, it's actually slower. For the first three up to 16, and then the improvement begins. I wonder if we have stopped it from inlining. So let's just have a look. Yeah, no, it's still inlined. Okay, so for big ones, we're doing a lot better. For short stuff, yeah, not so well. And in the sort, actually, the base case is only used down here. So we probably not improved it for the overall sort, but hey, we're just trying to improve insertion sort at this point, so let's focus on that. We should be able to do another improvement then, right? For very small arrays, it's just not good enough. But we could address that as a separate case. So let's do it. Let's go for some loop unrolling. All right, we know there's a lot of overhead of stuff going on here through the reads. We can make that read write business all a lot quicker. If b minus a is big enough, is more than 4, maybe, yeah, greater than or equal to 4, that's good. What we're going to do is we're just going to do a really fast unrolled loop sort, just the first 4. So we'll improve that a length 4 case. We probably won't affect the other cases nearly so much. But for length 4, let's make this super quick. So what we're going to do is you actually load everything in one go, right? We're going to read, but instead of reading in a loop, we're just going to unroll it and read everything explicitly. 4 things, 4 lines of code. Then we compute, and then we will write. So what we're going to do is just sort this. Like we've loaded probably these 4 variables into 4 registers. So this is not even using cache, this is even quicker. And then we're going to do the computation and then write them all out. So we can do the write out if we like. It's going to look just like the read in. We're going to write it all in one block. Compute. Oh, all right, let's do this. So we will sort the first 2 and then we'll sort the second 2. So if n1 is greater than n2, out of order, n1, n2 is equal to n2, n1. Put them in order. We do the same for the next case, which is with 3 and 4. And then we have to do some merging. We basically do a little merge of the two pairs, which is pretty easy. If n1 is greater than n4, then that's just done. The pairs need to be swapped. Now, what if n1 is greater than n3? It has to be moved up a bit. That means n3 must be the first. We're not sure where n2 is, so we'll leave it be. Okay, that's agreed. So n2 and n4 is a question. And finally, is there a finally? If n1 is greater than n3, n2. So n1 could be in the right place, but n2 might not. If n2 is greater than n4, otherwise, what if n2 is just greater than n3 but not greater than n4? Then only those two get swapped. Bit awkward, probably correct. Let's find out. Look, there's no speed up, but that's because I've done the really fast first case and then I haven't made use of it. So let's say this first. We want I begins at a plus 1, doesn't need to. I is equal to a plus 1. If we skip ahead, I can equal to, can it equal a plus 4 or a plus 5? It wants to be at index 1, yeah, now it's index 4. This is right. See what we get? I have high hopes. This should be very fast in the case 4. It's not that fast. 8 nanoseconds. In fact, it's doing worse. It's only helping here and it hasn't quite got us back to where we were before. Okay, let's take a look at what's called bounds check elimination. So bounds checking is what happens in a lot of programming languages when you access an array or a slice. It'll check the length of the array, make sure you're not addressing beyond it, like accessing memory you're not supposed to, and then throw an exception if there is. So we can avoid that. In a lot of cases, it's like you can tell from the code that it's not possible to overspill. And so let's have a look whether that's being used. We can do it in Golang just by adding a flag. Let's have a look. So we are from 13 to 41. Yeah, look at this, is in bounds. So that means it's doing a bounds check and a slice bounds check later down here. Okay, but is in bounds is being checked. It must be these writes and these reads. And language to language will be different how you chat with your compiler and let it know that it needs to do some work. Here it's pretty straightforward actually. What we can do for Golang, if you're addressing it with a variable, it will often not be able to work out that it doesn't need a bounds check. But if we tell it to address at an absolute, like a 0, 1, 2, then it should work it out. This is a bit specific. So language to language, not quite so general. We can just say length x, so that will let it understand about the bounds checks. And we want it to be at 1, 2, and 3. All of this compute remains the same. We will write to x. And AI ought to just do this instantly for me, but it's on the fritz. 0 less than the length of x. Okay. So with some bounds check elimination, oh, did we even do it? Actually, let's just check that we have the desired effect first. So at 10, yeah, does a bounds check there, and then the next one's at 45, which, It's not great because it's going to be doing a bounce check a lot. It's probably because of the -1. Might be able to get rid of that. Anyway, then it does slice bounce. So we haven't really sped all this bit up very much. It reckons it got slower after the bounce check elimination. But quicker because we eliminated the bounce checks down below. Fine. Let's chuck it in. An insertion, unroll, but with insertion, unroll, but with bounce check elimination is going to be slightly quicker. That's what I'm not sure what happened with the unrolling, to tell you the truth. To work on my optimization. Yeah, again, a fraction more expense early on. I do wonder if it's to do with, I'm not sure with the inlining, but we now got it to the best point here. So it is quickest for everything above 6. No, this one's faster for 16. Everything from 32 and above. Okay, so at this point, I'm quite keen to get in there and like mess around with sorting in general. I think maybe for the next video, if there is one, I will actually start to develop a much faster sort. We'll see if we can like do quicker than the Rust standard library, something like that. So we're pretty serious. If you want to see that, you have to comment, but smash something. Nothing. Smash some avocado on toast, like a scribe, literally. See you there.